Learn like a pro.
Ever wondered what's really going on inside an electric fan, or a blender, or even an electric car? Well, it's all powered by this incredible, invisible force that literally turns electricity into motion. And today, we're going to decode that exact blueprint.
All right, so here's the game plan. We're going to start by digging into this invisible pressure that actually creates the motion. Then I'll show you a super simple hand trick to predict which way things are going to move. After that, we'll figure out how to really crank up the power. And finally, we'll see how it all comes together to control a real machine.
So, first things first, where does this force even come from? Well, the secret is all about what happens when two invisible magnetic fields meet. So it all kicks off with this really fundamental principle. Anytime you have an electric current flowing through a wire, that wire generates its very own circular magnetic field all around it.
Okay, now let's take that wire and its little magnetic field, and let's place it inside a second, much more uniform magnetic field. You know, like the kind you'd find between the north and south poles of a big horseshoe magnet. And this is where it all clicks. The two fields, they don't just pass through each other, they actually interact. They push and they pull. See how the field lines get all squeezed together on one side? That creates this kind of high-pressure zone.
And that super dense region of magnetic pressure, it's not just an idea. It exerts a real physical push on the wire. It shoves it away from the strong part and into the weaker, less crowded area. It's kind of like squeezing a slippery seed between your fingers. It just has to shoot out from where the pressure is highest. And this whole thing, this entire chain reaction, from invisible fields crashing into each other to creating a real physical force that makes things move, that has a name. We call it the motor effect. So we know there's a force, but how on earth can we predict which way it's going to go? Well, it turns out the answer is this amazingly simple tool that you can, quite literally, hold in your own hand. I mean, knowing a force exists is one thing, right? But if you're an engineer, you need to know exactly which way that wire is going to move. Is it up, down, left, right? How do we figure that out?
The answer is something called Fleming's left-hand rule. Seriously, think of it as your own personal, built-in calculator for predicting motion. You just hold up your left hand, get your fingers at right angles, and your thumb is going to represent the direction of the thrust, or the force. See, each finger has a very specific job. Your first finger, you point that in the direction of the magnetic field that always goes from north to south. Then your second finger points in the direction of the current. It's really all about just lining things up. If we point our first finger along with the magnetic field lines and our second finger along with the direction of the current, bam! Our thumb just automatically points in the direction of the force. In this setup, that's straight up.
Okay, cool. So we can predict the direction of the force. But what if we want a stronger force? How do we get the most push possible out of this motor effect?
Well, the first thing you have to know is that the angle is everything. It matters so much. If the wire is running parallel to the magnetic field, there's basically no interaction. You get zero force. But if you can get that wire at a perfect 90-degree angle to the field, that's when you unlock 100% of the force.
So beyond getting the angle right, we've got two other main control knobs we can turn. Want a stronger push? It's pretty simple. You can either crank up the current flowing through the wire, or you can just use a more powerful magnet. Either one will give you a bigger force.
All right, let's put all this theory into practice. We're going to walk through a classic experiment that really shows every single principle we've talked about. And you know what? This is the basis for every simple DC motor out there.
So here's our setup. We've got a wire just hanging there so it can swing freely, right? And we're going to pass a current through it while it's sitting inside a magnetic field. The big question is, which way is it going to swing? Okay, let's run trial number 1. With our standard baseline setup, we flick on the power. And if you took out your left hand and applied the rule right now, you would predict an inward force. And guess what? That's exactly what we see. The wire swings inward. Now for experiment 2. This time, we're going to keep the magnet exactly the same, but we're going to flip the connections on the battery. We're reversing the direction of the current. And what happens? Well, just like the left-hand rule tells us, the force completely reverses, and the wire now swings outward.
And for our last test, what if we go back to our original current? But this time, we flip the magnet's poles. We're reversing the magnetic field instead. And we get the same result. The force reverses and the wire swings outward again. This just proves the rule works whether you change the current or the field.
And all of this really demonstrates the biggest takeaway here. The motor effect is our bridge. It's how we get from the invisible world of fields and electricity to the physical, mechanical world we live in.
It shows us that if you can control the current, you can control the machine. It's that direct.
So, the next time you hear that whir of a drone, or you feel your phone vibrate, or you see an electric scooter zip past, you'll know it's not just some kind of magic. It's the elegant, it's the predictable dance of the motor effect. That invisible blueprint of forces turning electricity into the motion that powers our entire world.